Welcome to Training Module 13, where we focus on testing and commissioning electrical grids, specifically transmission lines and power cables. This manual is designed to guide you through the essential procedures to ensure the reliability and safety of the electrical grid. As we look towards 2026, mastering these testing techniques is crucial for maintaining a robust and efficient power system. On this slide, we focus on the reference framework for testing and commissioning electrical grids. This serves as a foundational guide to ensure consistency and reliability in our processes. We rely on several key standards organizations, including IEC, the International Electrotechnical Commission, and IEEE, which is the Institute of Electrical and Electronics Engineers. Additionally, ASTM and NEMA provide important materials and manufacturing standards, while ANSI oversees national standards in the U.S. Other specialized bodies like SIGER, ICA, and KEMA offer guidelines specific to large electric systems, cable engineering, and electrical verification. It's critical to apply the most stringent requirement when there's any discrepancy between project specs, manufacturer instructions, and existing standards. Also, documenting which reference was used on the test sheet is necessary for transparency and traceability, so future reviewers can understand why certain results were accepted. This governance rule helps maintain accountability and quality throughout commissioning. Here we have the reference schematic for the phase checking and sheath test, conducted at 10 kV DC. This diagram is crucial for ensuring the integrity and proper functioning of the electrical grid during testing and commissioning. By following this schematic, technicians can accurately verify the correct phase alignment of conductors and detect any defects or faults in the sheath. This step is essential to guarantee safety and reliability before the system is fully operational. Keep in mind, this is outlined in the Commissioning Manual number 13-1, which provides detailed guidance on these procedures. On this slide, we focus on phase checking for conductor and sheath testing at 10 kV DC before energization. The goal is to verify conductor phase identity and ensure cable sheath insulation integrity across every link box. This is critical to guarantee safe and reliable operation of the electrical grid. We follow established standards such as IEC 60287, IEC 60141, IEC 60840, and internal work instructions, along with approved cable schedules and drawings. The equipment used includes a calibrated insulation resistance tester, or megometer, with voltage ranges up to 10 kV DC, leakage current indication, discharge stick, test leads, earth leads, and approved personal protective equipment. The testing script is methodical. First, we review circuit IDs, cable lengths, phase labels, link box numbers, and sheath bonding arrangements. Then, we apply lockout-tagout procedures, barricade the test area, verify absence of voltage, and install temporary earths as necessary. Next, for conductor phase checking, we apply 1 kV DC from one end and confirm phase continuity end-to-end by closing the far end switch, repeating this for each phase and recording resistance values. Before sheath withstand testing, we perform a 5 kV DC insulation resistance test for 1 minute on each conductor, recording baseline data. Then, we apply 10 kV DC negative polarity between the metallic sheath and earth for 1 minute per phase or sheath section, carefully recording leakage current. After each test, it is imperative to discharge the cable and sheath safely, restoring all earth connections, links, guards, and labels to their approved as left condition. Acceptance criteria include correct phase identity, consistent phase check resistance confirming conductor continuity, sheath leakage current not exceeding 5 mA where specified, and insulation readings that meet approved standards without any breakdown or abnormal trend. The result package must include completed test sheets, conductor ID records, link box references, insulation resistance and leakage readings, test voltages and durations, instrument calibration certificates, photographs, and witness sign-offs. A critical hold point requires witness confirmation of far-end switching status, open phases, temporary earth removal, cable discharge, and restoration of link boxes before the system is released for the next phase. Here we have the reference schematic for cable insulation resistance and capacitance measurement, which is crucial during the testing and commissioning of the electrical grid. This schematic outlines the standard procedure to accurately assess the cable's condition by measuring its insulation resistance and capacitance. Following this ensures that the cables are properly evaluated before putting the system into operation, helping to prevent potential faults and ensuring reliability. The schematic is detailed in Commissioning Manual number 13-2, which serves as the official guideline for these measurements. On this slide, we focus on testing and commissioning the electrical grid, specifically measuring cable insulation resistance and capacitance. The main goal is to confirm the quality of conductor insulation and capacitance characteristics for transmission lines and power cable circuits. We base our procedures on international standards like IEC 60228, manufacturer data sheets, approved route lengths, and detailed drawings. For equipment, we use a calibrated 5 kV insulation resistance tester, capacitance meter, or cable analyzer, plus discharge sticks and guarded leads to ensure safety and accuracy. The step-by-step testing begins by confirming cable identification, route length, conductor size, terminal markings, and test voltage ratings. Then, we isolate the cable from connected equipment, discharge it, and ground it before connecting the insulation resistance tester to each phase conductor. Applying 5 kV DC for 1 minute per phase, we record insulation resistance readings along with ambient conditions and any polarization or absorption notes. After safely discharging the cable to release stored charge, we measure capacitance using the same configurations and calculate capacitance per kilometer. These values are then compared against manufacturer data, design expectations, and historical records to identify any significant imbalances or deviations. Acceptance criteria require that insulation resistance meets approved minimums, capacitance per kilometer stays within manufacturer tolerances, and phase balance is maintained without unexplained trends. All results, including raw data, calculations, environmental factors, cable length basis, instrument calibration, and reviewed acceptance statements, form part of the evidence package. Finally, before sign-off, the review includes a hold point to verify the test voltage, duration, discharge status, calculation basis, and traceability of phase-to-record data, ensuring full compliance and reliability. Here we have the CM_P13-3 conductor conductivity and continuity schematic, which is a crucial reference for testing and commissioning electrical grids. This schematic provides detailed guidance on how to perform conductivity and continuity tests on transmission line conductors. Ensuring proper conductivity and continuity is vital for the reliable operation of the transmission lines, as it confirms that the conductors are intact and functioning as intended. This document serves as part of Commissioning Manual number 13-3, offering standardized procedures to maintain system integrity during the commissioning phase. On this slide, we're focusing on the conductivity and continuity test for transmission line conductors, a crucial part of testing and commissioning the electrical grid. The main goal here is to prove that the transmission line conductors are continuous, correctly connected, and electrically conductive from end to end. We follow specific references including IEC standards and approved line schematics to ensure accuracy. The instruments we use include a calibrated 1 kV DC insulation tester, or MEGR, continuity tester, low resistance meter, temporary shorting links, and insulated test leads. The testing procedure involves a series of steps starting with verifying the test locations and conductor tags, then applying lockout/tagout to ensure the line is fully isolated. Next, at the far end, we short the conductors together, and at the test end, apply 1 kV DC between conductors while recording the measured values. We confirm continuity with no unexpected open circuits or high resistance. Any suspect readings prompt a repeat test before removing the temporary links. Finally, we restore the conductor conditions, labels, and terminal covers. For acceptance, continuity must be proven across all intended conductors with stable and consistent values. No open circuits, wrong phases, or loose terminations should remain. The test results include a detailed evidence package with test sheets, far-end shorting confirmation, measurements, equipment certificates, photos, and witness sign-offs. Importantly, the hold point requires that installation and removal of the far-end shorting link be witnessed or independently verified before the line is re-energized, ensuring safety and test integrity. Here we have the reference schematic for the phase conductor insulation resistance test, which is crucial in the testing and commissioning of the electrical grid. This schematic helps us ensure that the insulation resistance of the phase conductors meets safety and performance standards before the transmission line becomes operational. Following this procedure carefully is essential for maintaining the reliability and safety of the grid. Now, let's talk about the phase conductor insulation resistance test for the transmission line. This test is crucial to verify the insulation resistance both between phases and between each phase and earth after installation and before energization. We follow standards like IEC 60287, IEC 60141, IEC 60840, and specific project specifications to ensure accuracy. We use a calibrated 5 kV DC insulation resistance tester, commonly called a megger, along with discharge sticks, earth leads, insulated barriers, and tools to measure environmental conditions. The testing process involves several steps. First, we confirm the cable identification, terminations, and isolation status of connected equipment. Then, we keep all 3 phases isolated from ground as per the test schematic. Next, we measure phase-to-phase insulation resistance between RY, YB, and BR using 5 kV DC for 1 minute, followed by phase-to-earth tests for each phase under the same conditions, recording stable values. It's important to watch for any sudden drops, unstable readings, abnormal discharges, or noises. After each measurement, we safely discharge every conductor and ground the cables to eliminate any stored charge. Finally, we compare the results against approved criteria and previous readings before proceeding to subsequent tests. The insulation resistance values must meet the minimum approved limits, readings must be stable, and there should be no signs of flashover, abnormal leakage, unresolved moisture, or grounding errors. All results, including test sheets, readings, discharge confirmation, and certificates for calibrated instruments, form the evidence package. Importantly, this test has a hold point where a reviewer verifies that all equipment is isolated and cables are discharged before personnel can access the area again. This ensures safety throughout the testing and commissioning process. Here we have the CM_P13-5 transmission line susceptance schematic, which serves as a crucial reference for conducting susceptance tests on transmission lines. This schematic is part of the commissioning manual number 13-5, guiding us through the proper procedures during the testing and commissioning of the electrical grid. The key point here is understanding how this schematic helps ensure accurate measurement and verification of the transmission line's susceptance, which is essential for maintaining grid stability and performance. On this slide, we focus on the susceptance test for transmission lines as part of testing and commissioning the electrical grid. The main goal here is to measure the capacitive susceptance of the transmission line circuit and verify phase consistency. This process follows standards like IEC 60287, IEC 60141, and IEC 60840, ensuring we use approved line data and calculations. For equipment, we need a single-phase 220-volt AC generator, calibrated ammeter, voltmeter, frequency meter, insulated leads, and temporary earths. The test procedure is detailed in several steps, starting with confirming that the line is isolated and prepared for a controlled test connection. We then isolate all 3 phases and focus on specific phase pairs such as RY for testing. The voltage is applied gradually while recording voltage, current, and frequency. From these measurements, we calculate reactance and susceptance using standard formulae. This procedure is repeated for the other phase pairs, maintaining consistent methods and records. The key here is to compare the phase balance and address any abnormal deviations before concluding the test. Acceptance criteria require that the calculated susceptance values are balanced and consistent with the cable or line design data, with no abnormal phase deviations. The test results are documented thoroughly, including readings, calculations, phase comparisons, instrument certificates, and the reviewed result package. Finally, there is a critical hold point where a witness must confirm source isolation, the rating of the temporary AC source, phase pair connections, and restoration of the de-energized state before proceeding. This ensures safety and accuracy throughout the testing process. Here we have the schematic for cross-bonding verification at link boxes, which is a critical part of testing and commissioning the electrical grid. This reference diagram helps us ensure that the cross-bonding connections are correctly implemented and verified according to the commissioning manual number 13-6. Accurate cross-bonding is essential for minimizing electromagnetic interference and ensuring system reliability during operation. On this slide, we focus on the critical procedure for testing and commissioning the electrical grid, specifically the verification of the cross-bonding test at link boxes. The purpose here is to ensure that the sheath cross-bonding links are connected correctly and that the induced currents in the link boxes behave as expected. We start by confirming the identification of each link box, reviewing bonding diagrams, and verifying the locations of GIS and GIB equipment, along with conductor terminations and sheath connections. Next, we ground cable screens at both ends and check that all safety earthing is properly applied. Following that, conductors are short-circuited firmly at the far end using the minimum approved temporary cable size, and then connected according to the cross-bonding schematic. The test current is increased gradually in controlled steps, balancing the phase currents to the required levels. Key measurements include using a calibrated clamp meter to record induced currents at every link box and relevant GIS or GIB locations. After the measurements, the current is reduced slowly, the test source is switched off, and all temporary links removed. Link box covers and labels are then restored. The acceptance criteria require that the measured link box current does not exceed 3 to 5% of the injected current where specified, which confirms correct cross-bonding connections and rules out any abnormal loop conditions. All test results are documented thoroughly and include test sheets, injected current records, induced current readings, photographs of link box status, instrument certificates, and witness sign-offs. Finally, there is a hold point where all temporary shorts, test connections, and restorations must be independently checked before releasing the system back to operation. Here we have the reference schematic for the VLF high voltage withstand test on power cables. This diagram is essential for understanding how to properly conduct the test during the commissioning and testing phase of the electrical grid. It's drawn from Commissioning Manual number 13-7, which provides detailed guidelines to ensure safety and accuracy in high voltage testing. Pay close attention to this schematic as it shows the key connections and components necessary for performing the VLF withstand test correctly. This slide outlines the power cable VLF high voltage test, a crucial step in testing and commissioning the electrical grid. The main goal here is to prove the cable's dielectric withstand capability using a very low frequency high voltage before energization. We follow specific references, including detailed work instructions, cable datasheets, and safety statements. The equipment used includes a calibrated 0.1 Hz VLF test instrument, leakage current monitors, discharge devices, earth leads, and all necessary safety barriers and signage. Our step-by-step testing process starts with confirming the cable rating, voltage, duration, and safety boundaries. Then, we isolate the cable from connected apparatus, install protective barriers and warning signs, and ensure proper earthing. We connect the VLF test set to each phase sequentially, applying the required voltage and monitoring leakage current for any signs of failure. After testing each phase, R, Y, and B, we discharge the cable completely before moving to the next. Once all tests pass without breakdowns or abnormal leakage, we normalize terminations and restore equipment. The acceptance criteria demand no trips, no abnormal leakage, and acceptable current readings as per factory or project standards. Our documentation includes the VLF test report, voltage and time records, leakage current trends, discharge confirmations, instrument calibration certificates, cable identification, and witness sign-off. Finally, remember the hold points. Establishing a high-voltage exclusion zone, test connections, discharges, and reconnections must all have formal witness approval to ensure safety and compliance. Here we have the CM_P13-8 phase sequence and rotation schematic, which is a crucial reference for testing and commissioning electrical grids. This schematic helps us verify the correct phase sequence and rotation of transmission line conductors, ensuring the system operates safely and efficiently. Proper phase sequence checking is fundamental during commissioning to prevent equipment damage and maintain system stability. This schematic is detailed in Commissioning Manual number 13-8, serving as a vital guide throughout the process. On this slide, we focus on the crucial step of checking phase sequence and rotation for transmission line conductors during testing and commissioning of the electrical grid. The main goal is to confirm that the sending end and receiving end phase sequences match perfectly before any energization or parallel operation. We base this procedure on standards like IEC 60287, 60141, and 60840, along with the approved single-line diagram and phase marking standard. Using calibrated instruments such as phase sequence meters, a three-phase 223/180 volt AC generator, or approved test supply, and voltage verification meters, we follow a detailed step-by-step script. This begins with verifying conductor labels against termination drawings and isolating the line. Then, we connect the test supply properly, measure phase voltages, and use phase sequence meters at both ends to read and compare rotation without changing leads. Any discrepancies, like conductor reversal or labeling errors, are addressed immediately before normalizing the system. After removing the temporary supply, we ensure grounding and restore all covers and labels. The acceptance criteria require that phase rotation and sequence be identical and align with the RYB designation, ensuring no mismatches remain. Finally, all test results, including readings, corrected labels, instrument certificates, and witness sign-offs, are documented as the evidence package. Importantly, this process includes a hold point. Both ends must confirm the same sequence before the circuit is released for energization or switching. This guarantees safety and operational reliability in the grid. Here we have the reference schematic for measuring both DC conductor resistance and earth resistance, which is an essential part of testing and commissioning electrical grids. This schematic, detailed in commissioning manual number 13-9, guides us through the correct procedures to ensure accurate resistance readings. Understanding and correctly applying this schematic is crucial for guaranteeing the safety and reliability of the electrical grid before it goes live. On this slide, we focus on the testing and commissioning of the electrical grid, specifically measuring DC conductor resistance and earth resistance. The goal here is to verify the cable integrity and ensure proper grounding readiness. We reference standards like IEC 60228 and internal work instructions, along with manufacturer data, route length, temperature records, and grounding specifications. The equipment used includes a digital micro-ohm meter, a calibrated earth resistance tester, auxiliary earth rods, test leads, a temperature measuring device, and approved personal protective equipment. The testing follows a clear step-by-step script. First, confirm cable details like length, material, size, temperature reference, and review test circuit drawings. Then, perform DC resistance measurements between phase pairs using the schematic connections, repeating measurements to capture raw resistance and conductor temperature. These readings are then converted to standard conditions at 20 degrees Celsius and resistance per kilometer. For earth resistance, auxiliary rods are installed in moist soil at specified distances, and measurements are taken at cable link boxes, ensuring recorded values meet project criteria. After testing, all test rods and leads are removed, bonding is restored, and any points of high earth resistance are addressed. The acceptance criteria require that temperature-corrected conductor resistance aligns with manufacturer or design limits, and earth resistance at link boxes does not exceed 10 ohms or meet specific project requirements. Finally, the result package includes micro-ohm and earth resistance readings, temperature correction worksheets, cable length documentation, instrument calibration certificates, photos, and witness sign-off. A critical hold point requires review and approval of earth electrode placement and temperature correction methods before acceptance. Here we have the reference schematic for the SVL insulation resistance and link box contact resistance test. This diagram is essential for understanding how to properly carry out these tests during the commissioning process. The insulation resistance test ensures that the electrical components are properly isolated and safe to operate, while the contact resistance test checks for any potential issues in the connections that could affect performance. Following this schematic carefully helps maintain system reliability and safety, as outlined in Commissioning Manual Number 13-10. On this slide, we focus on the SVL insulation resistance and link box contact resistance test, which is a critical part of testing and commissioning the electrical grid. The goal here is to verify the sheath voltage limiter insulation and the contact resistance in the link boxes, ensuring that sheath protection and bonding reliability are maintained. We follow a step-by-step script starting with confirming all tags, numbers, phase positions, and bonding arrangements, as well as the approved disconnection sequences. Before measuring insulation resistance, disconnecting links are removed as per the schematic. Then, we apply 2.5 kV DC to each SVL point and record the insulation resistance across all phases and link boxes. After the measurement, bonding links are restored and bolts tightened to the approved torque. Contact resistance at every link box connection point is measured using a microohmmeter. This process is repeated for all link boxes, and any issues such as high resistance, loose links, corrosion, or missing washers are thoroughly investigated. Finally, all connections, covers, labels, and seals are restored before the last inspection. The acceptance criteria specify that SVL insulation resistance must be at least 10 megohms, and link box contact resistance should be near zero and not exceed 20 microhms. All links must be properly restored. Importantly, there is a hold point requiring that link removal, restoration, and cover closure be witnessed to prevent sheath overvoltage risks due to incorrect bonding. We document everything with IR and contact resistance readings, photos, torque and visual inspection records, instrument certificates, and witness sign-offs, ensuring full traceability and compliance. Here we have the CM_P13-11 sequence impedance measurement schematic, which is a key reference for testing zero, positive, and negative sequence impedances. This schematic is essential during the commissioning phase to ensure the electrical grid operates correctly and safely. By following this manual, we can accurately measure sequence impedances and verify system performance. This helps to identify any potential issues early and maintain grid reliability. This slide outlines the testing and commissioning process for electrical grids, focusing specifically on the zero, positive, and negative sequence impedance test. The main goal here is to measure sequence impedance values for power cable circuits and validate them against protection and system study assumptions. We rely on key references like the approved protection study, cable models, and configuration drawings to guide the process. The instrumentation includes a three-phase variable transformer with up to 100 amps capacity, along with digital meters for power, impedance, voltage, current, frequency, and power factor. The testing script consists of 7 crucial steps, starting with confirming circuit accessibility and cable status, then connecting phases for positive and negative sequence measurements, gradually increasing current to around 25 amps and recording all relevant values. For zero sequence testing, the 3 phases are connected in parallel with a single-phase AC voltage source. Acceptance criteria require the calculated impedance values to be accurate, repeatable, and consistent with approved models, showing no abnormal phase imbalance or connection issues. Finally, all readings, calculations, model comparisons, and instrument certifications form part of the result package, with a critical hold point to review current injection levels, reverse terminal tests, and calculation sheets before formal acceptance. This thorough approach ensures reliable validation of the electrical grid's protection performance. Here we have the reference schematic for zero and positive sequence impedance tests on transmission lines, which is a crucial part of testing and commissioning the electrical grid. This schematic helps us understand and measure the sequence impedances accurately, ensuring the system operates safely and reliably. Accurate testing of these impedances is essential for detecting faults and maintaining system stability. This reference, from Commissioning Manual number 13 to 12, guides us through the necessary procedures to verify the transmission line's performance before it goes live. Here we have the procedure for testing and commissioning electrical grids using zero and positive sequence impedance tests on transmission lines. The key objective is to measure these impedances accurately with the CPC 100 and CPCU 1 test arrangement, ensuring the transmission line's validation against the approved model. We start by confirming all line identification details, grounding plans, and test setup configurations. For the zero sequence test, we short all 3 phases at both ends as illustrated and connect our instruments accordingly. After running the test, we record and verify the zero sequence impedance results. Next, for the positive sequence test, we configure the connections phase pair by phase pair, capturing consistent readings for each. All results must be compared against the approved transmission line model to confirm accuracy. It's critical to remove all temporary shorts and grounding connections afterward, restoring the line to its original approved condition. Acceptance criteria emphasize repeatability, traceability, and consistency without any grounding or connection errors. Finally, the test results and evidence package includes detailed reports, raw data, model comparisons, test photos, calibration certificates, and must be witnessed and signed off. Remember, the hold point requires independent verification of the shorting arrangement installation and complete removal before proceeding. This thorough approach ensures the integrity and safety of the electrical grid.